So with lesson 6, we're into our second day of doing max-min problems, trying to maximize or minimize a situation. And we saw on the first day how there were kind of 5 steps for working through a problem. I'm just going to go back and take a look at those steps. They were back on page 26. The first step was to maybe draw a picture. Second step was to set up your formula. Third step was to use a constraint to get rid of one of the letters on the right-hand side. Fourth step was to think about the interval, and then finally the fifth step was to actually go and do your calculus. Now there are only, so many different possible max-min stories out there. We're going to cover 10 of them by the time we've done 3 days of this, and here come another 4 today. This one talks about the story where you've got some external point out here. This point is 815, and we're going to try to take this point on the line here. I've just added that in there already. Try to find some spot constrained to be on the line that's as close as you can get to 815. I'm not allowed to put my point here. That would be cheating. It has to be stuck on that line that I've got there in blue. And I'm going to deliberately, totally get this off for a minute and say, hey, well, what about that spot? It doesn't look like that's the perfect spot, but we're going to let the calculus find the ideal location for that blue dot in order to make this distance between the 2 points as tiny as possible. I want to minimize that L. Okay, so I've already done the picture. I kind of have a feeling for what's going on, and I want to try to make that L as tiny as possible. The second step was to go and set up your formula. What are you trying to make tiny? Well, in the XY plane, if you want to try to measure a length between 2 points, it's really just some Pythagoras. And the formula ends up looking like this. We're going to say that the length of that line is just going to be the square root. Okay, and we're going to do nothing more than a little Pythagoras application here. So it's going to be the square root of x minus 8 squared. That's the leg along the bottom for that right angle triangle, plus y minus 15. That's the rise there. We're going to square that. So it's just doing some Pythagoras to figure out how far that will be. And our goal is to try to make that L as small as possible. So our goal, minimize this L that we have right there. Try to make it as tiny as we can. Well, the third step in the process was to use the constraint in the story. We are constrained to be on that line, so the y value for this point, it's not arbitrary. Once you pick the x, the y value for any point on that line is governed by the equation of that line, 6x plus 4. So we can actually go and replace that letter y with that, and now we can talk about this length as being purely just a function of x. Right? So I've got this. The length at any x that you choose to put your point is just going to be the square root. Actually, instead of writing it that way, let's go all calculus here and use some fractional exponents. So I'm going to do a square root. I'll use it as an exponent. We're going to have x minus 8 squared plus, and then here comes this constraint. Here, let's use some color to help you out. 6x plus 4 there, that's the same thing as y. And then we're going to go minus 15. And that gets squared. I have to take a root of all that. And there we go. I'm good to go. I've actually come up with an equation that using Pythagoras will measure how long that red line is for any x value that you pick. So as soon as you pick the x value, we can actually go and figure out how long that line will be, right? So we're trying to figure out, where exactly should we put this x value for that point in order to get that length to be as tiny as possible. Okay, well, I'm just going to tidy this formula up a little bit. I'm glad I've got that constraint rolling, but I think I can make this look just a little bit nicer. So this length, it's a function of x. Okay, doing some tidying here. I'm going to just tidy up that constraint. I've got x minus 8 squared plus, okay, what is this? This is like 6x minus 11 squared, and then I have to square root that. We might as well expand that out, make this look a little bit nicer before we go and do our calculus. So foiling this all out, looks like we're going to have an x squared. Twice we'll have a minus 8x, so minus 16x plus a 64. Then the other binomial, 36x squared. Twice we're going to have minus 66, so that's minus 132x. And then plus 121 when the two 11s square together. All that still needs to be rooted. Okay, I'm going to tidy it up one more time just before we go and think about intervals and do our calculus. We have got 37x squared minus 148x plus 185. And all of that needs to be square rooted. Okay, it's as good a time as any to talk about the interval for that x value. We have written this length in terms of just our choice for x for that point. And now you have to ask yourself, what is the smallest and the biggest value possible for that x value of this point right here? Now, I'm not saying that a really small or really big value is a good idea, but I'm just wondering, like, what is the upper and lower limit? How low can we make this x? Is it just 0, or could we even have a point out here that has a negative x to it? I think it's a bad idea, but I think we could actually have that x be as far back on the x-axis here as we want. We can go as far that way as we want, or even as far this way as we want. We won't get very short L's, but technically we could go that far. So the interval is actually a very soft interval here. We could go from minus infinity all the way up to infinity, both of which are some really bad choices for minimizing that length, but technically that's the interval. Okay, now it's time to go and do some calculus. Let's go and do our derivative. Let's go and do dl dx, or if you wish, L prime. So it looks like we've got a little blob here with a half on it there, so I'm going to do my chain rule. The half comes down, leave the blob, 37 x squared minus 148x plus 185, all that to the negative 1/2. Now multiplying by the derivative of that blob, that's going to be 74x and minus 148. And I'm wondering, when is that derivative equal to 0, or when is it busted? I'm looking for critical points. So let's go and rewrite this here a little bit. This dl dx, kind of wondering, could you ever be 0 or busted? Definitely worth a little rewrite. How about we write this as a 74 on the top. I'm going to do a little factoring here. That's x minus 2. Okay, so that's this binomial factored out, all sitting on top of this root down here. There's the 2, okay, and then we've got this root. 37 x squared minus 148x plus 185. And I'm wondering, could that ever be 0, or could it ever be busted? We're looking for critical points. Right now we're doing some calculus. And we're wondering, could that ever happen? Well, it is possible to make this ugly fraction equal to 0. That's if the numerator is equal to 0. And that'll happen when x is equal to 2. If you try just checking this quadratic out into the quadratic formula to see if it's possible to make it 0, that way you could have a 0 in the bottom and have a does not exist derivative, it doesn't actually work. There are no roots in there, no real numbers anyway, so that's actually a never. So really we've only got this one little critical value here. And analyzing this a little bit more, 74 is positive, the 2 is positive, this root's going to be positive, this x minus 2 could be positive or negative depending on where we're at. When you have numbers that are less than 2, if you put a number in here like say 1, this will be negative. So you have a negative derivative before 2, and then you'll switch over to a positive derivative later. So I think we do indeed have a minimum going on here, right? If you think about it, if you were to do a little graph of how long would the line be based on our choice in x, we're going to hit a minimum at 2. The derivative is negative all the time in its entire existence until you get to 2, then the derivative is 0, and then it's always positive later. So that is going to be the global best minimum, lowest minimum you can get happening there when x is equal to 2. Now we do need to go and find the full point. So I'm going to go back to my constraint and say, okay, the y was supposed to be 6x plus 4, and I have found the very best x to actually be a 2. And I'll go and add 4, and that ends up being 16. So the closest point you can get on that line is 2 for x and 16 for y. That's going to make that length as tiny as you can get it. Okay, so that's our first of 4 here for today. The next couple are some neat ones about geometric shapes. Example 6 is going to be about a Coke can, and we're going to try to design the perfect Coke can that will use the least amount of aluminum. And maybe we can maximize the profits for the Coca-Cola company. We definitely have to make sure we hold the right amount of product, but we're going to try to use the least amount of aluminum to do that. So it says, go ahead and find the height of a cylindrical Coke can that requires the least amount of aluminum. Kind of think of it as a surface area thing. Least amount of aluminum to construct. The can must have sides that are 2 times thinner than the top or the bottom. So that's true for cans. The sides are quite flimsy, but the top and bottom are a little thicker. And the volume must be 355. Got to hold that amount of pop in there. Well, there really are only 2 numbers to describe the overall size of a cylinder. We're going to have the radius for that circle at the top or the bottom, and then we're going to have some height to the structure. Okay, and so we're going to try to find the perfect Coke can to do this. This one here, we're trying to minimize that surface area. There's a bit of an issue with the thin sides on the edge, but we're going to make sure we have the right amount of volume in there. So the constraint in this story is making sure that all that Coke can actually fit on the inside. So I've already got my little picture drawn there. I want to jump right into the constraint. The volume for a Coke can is going to be pi r squared times h, and that has to hit 355. And I'm going to use this to get rid of one of those letters. I think the nicest one to solve for would actually be h. So when I'm ready, if I don't want to have h in my math, I could actually substitute out the h and put in 355 all over pi r squared. That just gives me an option not to have h's. Okay, let's talk about the amount of aluminum we need. Think of the A here as being for surface area. I'm going to look at the surface area of the cylinder. With one little change, I'm going to thin up the sides. So normally for a cylinder, you would say, hey, look, there are a couple of circles here. There are a couple of pi r squareds, one for the top, one for the bottom. And traditionally, you would just say, okay, the label along the side is 2 pi r for the distance around multiplied by h. But this one has kind of a neat little story to it. It says, you know, the sides can actually be twice as thin, so they're going to have less aluminum there. And so I don't want to count that aluminum as aggressively, and that's just this little bit of info there. These stories don't always have that, but this one's definitely talking about it. So I'm going to just throw that in this way. So it's kind of like I'm finding surface area, but I only want to count the area on the side as half because the aluminum will be so thin there. Okay, well, let's just tidy up our formula. Finding that formula was usually the second step, and I've got my constraint, which is going to be step 3. I'm going a little bit out of order, but I think it'll be okay here. Got 2 pi r squared plus, well, with this little twice as thin thing, I'm just going to have a pi rh going on over there. Again, 2 variables, don't really want that, right? So that's why we use this constraint. So we have 2 many variables. In second year university, you'll look at how you can have multiple variables over here on the right hand side, but we don't want that right now. So I'm just going to make a substitution. I'm going to use that constraint and say, hey, you know what? I want to make sure I have the right amount of volume here. So how about we rewrite this? 2 pi r squared plus pi r, and then in comes this constraint. Instead of h, how about we put in here 355 divided by pi r squared. Now before I go and do all my calculus, I should think about an interval, and then I should clean this up. Let's clean it up first. So the amount of aluminum, it's kind of surface area, but with that little 1/2 modification in the story, and I've got it expressed as a function of r, it's equal to 2 pi r squared. Now tidying this up, the pi's cancel. The r's reduce a bit. I'm going to have 1 r in the bottom and the 355 hanging around. You know, you could write it this way. I don't really like fractions, so I'm going to write that as a power, like that. Okay, I'm basically ready to go, but I do want to think about the interval. what is the smallest and the biggest amount possible for that R. So now that I've got it down to one variable, it's time to think about that choice. I do have to make sure I've got that Coke inside, the 355 cubic centimeters or milliliters. And the interval for R, well, I can't have negative R's. That doesn't make any sense at all. I could bring the R right down to just about 0. It'd have to be a very tall Coke can, but pretty much 0. It couldn't be 0 where I wouldn't be able to get any Coke in there. So how about 0 with a soft edge? And then I'm not saying it's a good idea, but you could actually have an incredibly wide Coke can. It would just have to be very short. It's probably going to use a huge amount of aluminum, but officially it could go all the way out to infinity. So soft edges, not a lot of interesting endpoints going on there. So I'm going to hope that the calculus can actually find it when I go and do my derivative. I'm pretty much ready to go. I've got my function. It's time to go and do a derivative and see what the calculus can find. So I'm going to go and do dA dr. And when I try that out, I'm going to end up with 4 pi r minus 355 r to the negative 2. So that negative 1 comes down, changes that plus to a minus, and then r to the negative 2. Now you can rewrite that, if it helps, 4 pi r minus 355 all over an r squared. And I want to pause here for a second just to sort of make it totally clear what we're trying to do, where we're trying to go with this. This function that we've got right here talks about how much aluminum it would take based on choices for R. And ultimately what's going to happen is if you were to graph this amount of aluminum, kind of like surface area with that little twice as thin modification, and R, somewhere in there, I'm not sure exactly where it's going to be, but somewhere in there there's going to be this minimum. And we're trying to find that. And that's going to be a flat spot on the graph. Right? It's either going to be a flat spot or a little cusp in the graph. So we're hoping that the calculus can go and find that spot where things are flat. And as I stare at this thing, it's really hard to know, like, where is that equal to 0? So I'm just going to rewrite it with a common denominator. Okay, so dA dr, my derivative, talking about the slope of that graph. If I go with a common denominator of r cubed, I think that would be helpful. So this first term needs a little kick with an r squared to get there, and you're going to have 4 pi r cubed by the time you have the common denominator, minus 355. And I've got the wrong denominator down there. Sorry, that's going to be a squared. There, fix that. Okay, critical point. I'm wondering, could that ever be 0, or could you break it? Well, actually, you can do kind of both. The 0 would be if the top of that fraction is equal to 0. And that would be just the right r value, so you can cube it, and then you'd have this whole binomial turning into 0. And that'll happen if the r is equal to the cube root of 355 all over 4 pi. Now, when I tried that out on my calculator just to see what it would be as a decimal, it was 3.0456 centimeters, which is pretty darn close to how big the radius actually is for a Coke can. Now, trying to make this derivative busted. Well, I could make that r equal to 0, at least I would think so, but then I look and go, uh-oh, nope. This thing says the r has to be slightly bigger than 0, otherwise it doesn't make sense. So yeah, I tried, but actually don't have to worry about that at all. That's not even really an issue. And so we've actually only got this one critical point for the r, for our graph of A versus R, and that is going to be the minimum amount of aluminum. We've found the very best radius, but now we have to go and find the best height. And so we had that constraint, right? We knew that height was equal to 355 all over pi r squared. And I'm going to take that for my r and just go and embed it in right there and see what I get. And when I tried that out, I ended up with 12.1823 centimeters. And if you check it out, that's really, really close to what the radius and the height for the perfect Coke can is. It's pretty close to what you will actually find for a Coke can. Now, if you look back at the top of the question, it said, go and find the height. This was the one thing that they wanted. So you always want to make sure you're answering their question, right? And so that was their question, and there's the answer for it. Now, looking at this whole thing here, this whole page, for this one, we were trying to get the area, and I say that casually because of that twice as thin thing, but we were trying to get the area very small, surface area, but we had a certain amount of volume on the inside. And when we go and look at example number 7, it's kind of the same thing, but it's the other way around. We're going to try to maximize the volume, but for a given amount of area for the material. So it's kind of the reverse of what we're about to do. And so here it is. It says, find the dimensions of a cylindrical tuna can that contains the largest volume possible using only 96 pi centimeters squared of surface area. Now, at first glance, I look at it and I'm like, are you serious? Like, what's this pi doing there? Well, it turns out that's actually a bit of a gift. It's actually going to make the problem work really, really well. So the previous question, the goal was to minimize the area with that little twice as thin caveat. And now for this one, we're going to spin things around a little bit. The goal for this question is to maximize volume. Okay, well, it's some sort of cylindrical can, so let me just kind of get ready to go here. And so here's my can of tuna. Looks kind of like this. There's a certain radius to it, and there's a certain height to it. And I want to try to make that volume as big as I possibly can. So I'm starting to think about the equation for that. Okay, volume. U are pi r squared times h for a cylinder. I want to make that big, right? That's my goal. Make this V, this volume, as big as you can. But you can't just go and make the R and the H as big as you want. There was a constraint in the story. They said, no, there's only a certain amount of aluminum to play with. So let's go and get that set up. So the two circles plus the label, they have to add up to 96 pi. So you would have 2 pi r squared, there are the two circles, plus, here comes the label, 2 pi rh. That has to be 96 pi. Oh, I can see why they put the pi on there. It's actually really kind. I can reduce these pi's now, kind of cancel them out of there. And I'm going to take this constraint that right now just looks like this. In fact, why don't we cancel a 2 as well? We'll divide by 2, and we'll end up with r squared plus rh is equal to 48 when we divide by 2. So I'm looking here and I'm going, too many variables over on that right-hand side. I got to get it down to just one. So now I start looking here and I'm going, okay, well, which is the easiest variable to isolate for, to get by itself? And here I think it would probably be the h. I can get that by itself pretty nicely. It looks like RH would be 48 minus r squared, or h would be 48 minus r squared all over an r. Okay, I'm going to use that instead of this h here, because I don't want to have too many variables over on that right-hand side. So rewriting this volume formula that I'm trying to make really big, I would have pi, the r squared, and then here comes this bit of a mess. But the good news is at least it's not another variable. It's just the same variable, it's just the r. Oh, that's a bit messy. Tidying this up, let's just make this look better. When we go and actually multiply this through, we're going to end up with a 48 pi multiplied by r, and then subtract. Okay, what happens when we bring this into here? Well, we're actually going to have an r to the fourth on top of an r. We're going to have an r cubed. We're going to have a pi in there. So minus pi r cubed. Okay, we're getting close, right? We're about to do our calculus. We've got our volume formula. We're going to try to make that V really big. That's our goal. We have gone to the trouble of getting this all down to one variable on the right-hand side, just r. it's now time to talk intervals. What is the absolute smallest and absolute biggest value you can have for R? Okay, so this is choices for R. Well, you can just about go to 0. So I'm going to go 0 with a soft edge. And you might think, oh yeah, and yeah, I've seen this before. You could go to infinity up on the top end, but actually you can't. The biggest you can make the R, it turns out, is the square root of 48. Hard edge. And so you might look at it and go, whoa, 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 where did this come from? Well, that would be if you make the R as big as you can, and you use, I'm going to mess my picture up here a little bit, you use all of your surface area of material, of metal, to just make these two circles, the one for the top and the one for the bottom. So that would be putting 48 pi centimeters squared into each one. And so what I did is I just kind of went to the side of my page and said, okay, well, if I was going to go, pi r squared is equal to 48 pi, what does that mean? Well, the pi's cancel, and then I took a square root, and that's where this root of 48 came from. So I don't think that's a very good way to package tuna, because there would be 0 height, and you'd have no tuna left in there. But it is technically the biggest value you could have for R. All right, let's go and do some calculus. I'm trying to picture now this graph in my mind. I'm just going to sketch here for a second. Like I've got volume, choices in R, somewhere there's going to be a top, and I want to find that top. And that's going to be a time when the derivative is equal to 0. So let's do a dv dr. Okay, well that would be 48 pi minus, the 3 comes down, 3 pi r squared. And I'm wondering, it's time to do critical points. I'm wondering, could that ever be 0, or could that ever be busted? Well, it can be 0 if you just take that to the side of your page and just say, okay, 48 pi minus 3 pi r squared equals 0, and move the 3 pi r squared to the other side, divide by 3 pi, take a square root. It actually worked quite nicely, and you'll see that, yeah, you can get that equal to 0 when the R is equal to 4. And you can never break this thing. Okay, now I don't have a lot of room on the page, but basically all I did, I'll just doodle here for a second. I just said, okay, could 48 pi minus 3 pi r squared, could that be nothing? And I went 48 pi is equal to 3 pi r squared. I divided by 3 and I divided by pi, and I got 16 is equal to r squared. Took a square root and got the 4. I wish I had more room and I could leave that there, but I need some space, so I'm just going to take that away. But that's all I did to get that 4. All right, what I would do now is I would check out the contenders that I've got. I've got a couple of different ones that I can try. I could try that R value of 4 and see what I get for volume, or I could try that R value of root 48. Just put them into the original story right here, right? And just see how much volume do I actually get. And the answer, when I put 4 in for R, I get a pretty decent volume. I get 128 pi for my volume for my tuna. And when I put in that root 48, I get nothing, no tuna at all, right? And all I'm doing here is just putting in my contenders for R. So clearly this is your best volume right there. 128 pi is more than 0. And so I'm pretty much done. I have found the best radius, except the question said go and find the dimensions. Oh, okay. So the dimensions, I need to have the h as well. So I go back to my constraint. I know that the h was equal to 48 minus r squared, all on top of an r. And I've now learned that the r should be 4, right? Saw that right here. So 48 minus 4 squared, all on top of 4. That ends up being an 8. So here are your best dimensions. If you want to get a lot of tuna in the can, let the R be 4 centimeters and let the H be 8 centimeters. That's the best you can do. Okay, now that leaves us with one more story to take a look at. Kind of similar to ones that you might have done in Math 11 when you were looking at parabolas. And we're going to let our calculus actually make this a lot nicer than doing it the Math 11 way. So it's a little business story. It says low-cost Leibniz Airlines currently charges $145 for its flight to Toronto and currently sells 92 seats on its 112-seat aircraft. And it's been determined that for every dollar they increase the ticket price, just based on some market analysis, one less person will choose to fly with them, right? Because people are like, it's too expensive, I don't want to fly. And you have to try to figure out the perfect ticket price to try to make as much revenue as you can. That's your goal. And so I'm just going to set up some variables here. I'm going to let R be my revenue, right? The money coming into the company. And my goal is to maximize that. I want to try to get that R to be as big as possible. Okay, well, how do you calculate the revenue? The revenue is actually, the amount of money coming in. It's just the price you're going to charge multiplied by how many people choose to actually go to your company. And so sure, you can raise the price, but as you raise the price, the number of people go down. And it's not clear whether you'll actually make more money or less money. The converse is true too, right? If you lower the price, then more people will show up. So maybe by lowering the price and having more people show up, you might actually have more money coming into your company. We have to go and play this and just as a manager figure out the best price to charge. So I'm going to assume that we're going to increase the price. Okay, the wording is kind of like that in the problem. So let's let X equal the increase in the ticket price. Right now we're charging $145. Let's let X be how much we want to up that by. So if that's the amount the ticket goes up by, then 145 plus X is going to be the new price. Because we were already charging $145. Now we're going to up it by some amount we're not sure of called X. But the number of people will be less. We used to have 92 people, and for every dollar we up the price, that's called X, we're going to lose a person. So 92 minus X is our new people count in our new company, right? As we go and kind of restructure everything and change our ticket price. Okay, well, here we go. So R would just be, I'm going to do this, just price multiplied by people, right? That's my plan. So my price is $145 plus X. And my new number of people go flying with my company here is 92 minus X. Oh, that's a product. I don't really want to do the product rule right now. So I'm going to go and just FOIL this all out. And I end up with 13,340 plus 92X minus 145X minus X squared. Okay, tidying that up a little bit more. The amount of revenue as a function of ticket increase, right? So I can just throw in different ticket increase prices and see exactly how much revenue I'm going to make. That revenue as a function of X is going to be negative X squared minus 53X plus 13,340. Okay, we're there. We now have this revenue function. Let's go and do our calculus. Right, I want to try to get the top of that curve. If I can imagine there being a little graph out here of, hey, how much money are you going to make based on our increase in ticket price? I want to get the top of that curve, right? Find out where I'm going to make the most money. So I'm going to do a little derivative here. I'm going to do a dr dx. So I can find the flat spot on that curve. And I end up with negative 2x minus 53. And I'm wondering, as always, looking for critical points, could I make that 0? Could I find a flat spot? Or could I make it all busted? Could I find a little cusp in the graph? You can't break it. So the D and E option is never going to happen. There's no cusps in the graph. It's, after all, just a nice little upside down parabola. But there is a way where you can get a flat spot on the graph. And that's when x is, now this is interesting, negative 26.5. Whoa. Okay, so x was supposed to be how much you raise the ticket price. And we're actually getting some really cool information here. This minus sign is saying, hey, we should lower the price. If you have a negative increase, you've actually got a decrease. Looks like of $26.50. But there's a catch. We've actually missed something, and I've done this deliberately because I just wanted to see whether any of you would notice. I went right from setting up my formula, using my constraint, right, about people leaving the company, to get it down to one variable, and then I dove right into doing the calculus. But you know what I never looked at? And I've left some space over here for it, is the interval. What is the interval for x? We're trying to write this whole story in terms of x, how much you raise the price by. And you might think, well, the sky's the limit. You can do whatever you want. But it's not true. The lowest you can make x is actually not as low as negative 26.5. It's actually minus 20, hard edge. And I'll tell you why in a second. The biggest you can make x and have it make sense in this story is 92, hard edge. Okay, so where are these numbers coming from? Because the math is saying, no, lower the ticket price by $26.50. So many more people will come, it'll be worth it. But you got to remember that when you lower the price, every time you lower it by $1, based on our market analysis, one more person will fly. And we've only got 20 more open seats, right? Like we're already getting 92 people to fly. There's only 112 seats on the airplane. So as soon as 20 more people come, your plane's full. There's no point, lowering the price anymore because people can't get on your airplane. They're going to want a refund. So actually, this minus 20 here, this is a lowering of your price by $20, and that's when you'll have a full plane. The 92 would be an increase in $92, and at that point, 92 less people would fly. Well, you only had 92 on the plane at the beginning, so now you've got an empty plane. People are like, yep, I don't want to fly at all. There's no point going with a more expensive price than that because you'd have negative people. That doesn't make any sense. So it turns out it's a little bit weird, but based on the interval, we actually need to reject this answer and say, nope, we can't take it. We're going to have to actually go with just going as far as we can to the endpoint. You would basically at this point check out nothing but the endpoints. You would say, okay, what's my revenue if I go with minus 20? What's my revenue if I go with 92? Just checking out the endpoints. If you go with minus 20, you actually make $14,000 per flight. And if you go with an increase of 92, right, these are X values, these are increases in price, you have no money because nobody flies at all. So I'd go with that minus 20, the very best X in this story is actually a negative 20, and so your best price is actually going to be a $20 drop. We were $145, so we're going to go to $125. Now here's another way to look at that. I'm actually going to graph this revenue function right here. Okay, if you're sitting there going, I don't get it. Why didn't we go with the negative 26.5? Well, let's just briefly graph this revenue function and see how it looks. Okay, get all that out of there. Okay, so this is negative x squared minus 53x plus 13,340. It's going to take me some time to get a window that lets me see this whole thing. I'm just going to start off with my good old zoom forward. I'm probably not going to see a single thing. All right, so I got to start zooming out. So here we go, zooming out until I can see some stuff. Okay, it's going to take some time. I'm going to zoom out again. I'm going to zoom out again. This parabola's out there somewhere, right? I just have to find it. Okay, there we go, starting to see it. Okay, I'll go out a little bit more. Okay, so I can see the parabola, but I can't really see the top. So let me just start manually changing these things here now. I'm going to change my Y min and Y max. I want to go all the way up to, let's say, I don't know, $15,000. Tick marks every, let's go every 1,000. See if this looks any better. Okay, so there's my parabola. The x-axis is a bit of a mess. Let's change this a little bit more. Let's just go from minus 200 up to 200. Tick marks every $50. I'm going to go a little deeper on my y's, maybe down to minus 2,000. Okay, there's my parabola. All right, and I'm trying to figure out, all right, where's the very peak of this parabola? Right, I've got that. Oh, actually, this is not even the right parabola. I was kind of wondering. It seemed to be centered at the origin, or centered at x equals 0. I'm going to have to sneak this in. This could shift my picture here a little bit. Not by much. Okay, so if I was to just say, well, where is the maximum? You know, calculate the maximum value. Right, so my left bound. Okay, I'm going to wander way back here. There's definitely a left edge. And way over here is a right edge. Yep, and a guess. Okay, I'm going to let this thing do its thing. And it's found the best story. It says, yeah, you should go with minus 26.5. And you'll make $14,042. That's better than my $14,000. But this assumes that I could actually lower that price and still fit people on the airplane. My window, my interval for X, for choices for X, actually can only go from minus 20 to 92. So watch what happens when I constrain my story that way, right? If I say, oh, okay, negative 20 up to 92. So you won't get to see the vertex of this parabola. The vertex of the parabola is just back to the left here, and it's kind of out of view. I wish we could go a little farther back, but we don't get to because there is a little bit of a higher peak out there. So the best thing we can do are the endpoints. And when I go and check out the actual value for this story at negative 20, well, that's a pretty good amount of revenue. Or at the other end at 92, that's no revenue at all. So the best story is when we go with that minus 20. So you got to be careful with that full airplane. Sometimes those intervals will actually catch you. They're actually going to be kind of an important thing to go and take a look at. And that was certainly the case here. So we've got just a couple more examples to do for looking at max min, and we're going to save those for the next video. And this is the end of this one here. We'll do this even more max min next day, where we'll do just a couple more of those.